Something a little different this time as we start types of aqueous solutions and solubility. I'm going to show a little video.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
All right, now let's talk about that a little bit more. So in your picture here for sodium chloride, which is a solution which is a strong electrolyte, the light bulb lights up. And that is because ions in the solution, the sodium and the chloride ions, can move. Because ions in the solution can move. And if we were talking about electricity for a minute, what we would say is that in the wires that plug into the wall, some of the electrons are moving, let's say this way. They move through the metal, and then in the solution, the ions carry the charge. In the wire, electrons carry the charge, but in the solution, ions, sodium ions, chloride ions, actually move through the solution to ferry the current from one side to another. Then those charges, that current, that charge, if you will, can then complete the circuit and light the light bulb. And that's why the light bulb lights up for sodium chloride. In sugar solutions, there are no ions and there's no current. So think of this as there's no movement of charge and you can't close the loop. Well, that's an introduction to it. And to really understand electrolytes, we need to talk about our second reaction type, a dissolving reaction. A dissolving reaction for sodium chloride looks like this. Sodium chloride, which is a solid, goes into the aqueous phase. And because sodium chloride is a strong electrolyte, it breaks up into ions. And these are the ions that we're familiar with, sodium ions and chloride ions. These ions will always be familiar to us. And it does this for sodium chloride 100% because it is a strong electrolyte. Now, let's talk about what it means to be in the aqueous phase when something is dissolved. We're going to look at sodium ion. And the sodium ion, when it's dissolved in water, will have what's called a hydration shell of water molecules around it. We'll talk about this later in the course, but water itself has a bonding structure or a Lewis structure like this. And as most people know, but no worries if you don't, we explain this totally later in the course, has a slight negative charge around the oxygen, and that slight negative charge will be represented by a lowercase Greek letter delta minus. And in case you can't see that, it's like a D or a squiggly D here with a minus sign associated with it. It's actually a lowercase Greek letter delta that we draw in this way typically, although there are other ways to draw lowercase Greek letter delta. Anyway, the oxygen's partially negative is how we pronounce this. The hydrogens are partially positive. And that means that if you have a sodium ion that is dissolved in water, the oxygens will tend to be closer to the sodium than the hydrogens. And you just want to draw some sort of shell. Could be 4, could be 5, could be 6 of oxygens closer than hydrogens, forming some sort of shell. The key part of this picture is that the oxygens are closer than the hydrogens on average. And this is a dynamic picture. Those water molecules are moving around constantly, but on average, this is a good picture. On the other hand, chloride, which is a bigger ion, is a negative ion as well, and for it, the hydrogens are closer. And whether you draw 1 hydrogen or 2 hydrogens, as long as on average you can tell that the hydrogens are closer than the oxygens, because it is just a schematic picture to represent the fact that the partial charges in water are what help sodium chloride dissolve into the aqueous phase, and the attractions between those ions and the water molecules. And these are good pictures of hydration shells. These are simple pictures because they're just monatomic ions, positive and negative. But that's what's going on. That's what it means to be aqueous. Aqueous means surrounded by water molecules in a hydration shell. Now, as we said, sodium chloride is a strong electrolyte. So strong electrolytes dissolve 100% into ions. I'll put a little colon here. Dissolve 100% into ions. So when dissolved in water, their solutions conduct electricity. Well enough to light a light bulb brightly. Okay. Sugar, on the other hand, is a non-electrolyte. Now, sugar does dissolve. I prove that every morning when I put some into my coffee, and I do not taste sugar crystals because it dissolves. Sugar is a non-electrolyte. It dissolves as whole molecules. So, strong electrolytes dissolve and break 100% into ions, because the dissolving is not the difference here. They both dissolve. But the strong electrolyte dissolves and breaks into ions. The non-electrolyte dissolves and stays together as whole molecules. So if I were to write a dissolving reaction, for sugar, and we'll go with, there are many sugars, but let's go with table sugar, C12, H22O11. It would have the solid phase as a reactant, and on the product side, it would have an aqueous species, but the aqueous species is just whole molecules. So yes, it dissolves, yes, it becomes aqueous, Yes, it has a hydration shell that is much, much more complicated, but the same idea as for the sodium or chloride ions. There are water molecules surrounding this in a hydration shell. Um, but so it is aqueous, no ions, no conducting electricity. The light bulb does not go on, but it does dissolve. All right. Now let's talk about weak electrolytes. Acetic acid is a weak electrolyte. A weak electrolyte dissolves and breaks into ions less than 5%. And less than 5% could be 0.1%, but they're all less than 5%. Dissolves and breaks into ions less than 5%, and solution conducts, there are enough ions that the solution conducts electricity a little bit. And I'll just use the term weakly here, and the light bulb lights weakly. Meaning dimly, not weekly on Tuesdays. Now, acetic acid is a weak electrolyte. We've talked about acetic acid before. It is CH3COOH, where we've talked specifically about the COOH group before. And acetic acid in its pure state is a liquid at room temperature. And if you dissolve it, all of the species on the the right-hand side will be aqueous. That's what dissolving means. If I ask you to write a dissolving reaction, all the products will be aqueous. The question is, will they be ions? Will they be molecules? Will they be a combination thereof? And this one is tricky to write what the products are, but let's do it. The first product is acetic acid dissolved as aqueous, and this is greater than 95% of the species in the solution, of the things in solution. Then less than 5% would be the ions, and the ions in this case are going to be H+, and CH3COO-. And so for these two, let's see if we can do this, they'll be less than 5%. So a small portion breaks up into ions. These portions add up to what we originally had, but now they're aqueous. Now this will happen for, and what are weak electrolytes? Weak electrolytes are weak acids, and weak bases. Weak acids have the COOH group, and weak bases have the NH2 group. Now, here are some solubility rules to memorize. At least when this was a face-to-face class, you should have, I've put those solubility rules on your nomenclature sheet for you to use in the online version of this course. So we will just have to know how to use them. We will not have to memorize them. So let's say solubility rules to know how to use. For example, all common compounds of group 1 and ammonium ions are soluble. I know I have my periodic table around here. There we go. Got away from me a little bit there, but all right. So all common compounds of group 1 and ammonium ions. Here's group 1. So anything that has lithium, sodium, potassium, rubidium, cesium, we won't see francium, or ammonium, where ammonium is NH4+, are soluble. Anything with all nitrates, acetates, perchlorates, and chlorates are soluble. All binary compounds of the halogens, other than fluorine, with metals are soluble, except those of Ag, mercury, 1, and lead. So for example, according to this, so let's see, calcium chloride would be soluble, which means it would be aqueous in water, but silver chloride would be insoluble and therefore a solid phase. So soluble materials are aqueous in water, and insoluble materials are solids. Okay? And then let's do rule number 5, except for rule number 1, which says all of these things are soluble. Carbonates, hydroxides, oxides, etc. are insoluble. What that means is ammonium carbonate is soluble and therefore aqueous when dissolved in water, but calcium carbonate would be a solid. So that's a little guide on how to use these rules. I'm going to keep my periodic table a little closer. In summary, we have this picture. When you have sugar, it will dissolve, so it will be aqueous. It's a non-electrolyte. There are whole molecules, and therefore no light bulb is lit up. For a strong electrolyte, we have sodium chloride. Those sodium and chloride ions break up and carry current between the two pieces of metal in there, or this looks like graphite, but the two conductors. And the light bulb lights up brilliantly or brightly, strongly. Weak electrolytes, we have mostly whole molecules, every once in a while some ions, and those ions allow the light bulb to light dimly or weakly.